Welcome. This is the second derivative test. All right, so let's take a look at this example. In the graph of f below on the interval a through q, list the open intervals on which the graph of the function is concave up and concave down, and then determine the inflection values. Develop criteria we can use analytically to find inflection values from the equation of a function. All right, so concavity switches where the second derivative is 0 or undefined, and those are our inflection points, right? So inflection points are where we switch concavity. All right, so let's take a look. All right, so our graph from A to B is concave down. Where's my C? And right here is the inflection point. I'm going to put IP for inflection point. And let's also determine why there is an inflection point. Is it because the second derivative is 0 or the second derivative is undefined? In this case, it's because the second derivative is 0. Right? It'll be kind of obvious when the second derivative is undefined. I was just looking really quickly in your notes to see, yes, this is in your notes, by the way. All right, so here our second derivative, oops, doesn't look like there's two prime marks there, is 0. All right, and then here the graph is concave up from B to C, and we have another inflection point. All right, whoops, well, it's trying to be in the right spot. There we go, there's the inflection point. And again, we have an inflection point there because the second derivative is 0. All right, and keep switching colors here. The graph is concave down. So notice that where there's an inflection point, the graph does shift concavity. Our next inflection point is right here. And look what we have. We have a cusp. So here we have an inflection point. But this is because the second derivative is undefined. And then continuing along. So by the way, we're going to write at the bottom where the graph was concave up and concave down. We're just going to label it on the graph and then we'll list it. All right, so now the graph is concave up. All right, it looks kind of like a cup. That's how you know it's concave up. And right here, all right, we have not an inflection point because the graph is still concave up. Notice there's no change in concavity at E. We go from concave up to concave up. All right, so not an inflection point, but the second derivative here would be undefined because of the cusp. Right? And then last, we have one more inflection point. That's really odd. I don't know if you can see that, but I cannot see my colors, and I wanted to switch to purple. I don't know what's going on with my board. I just noticed that today. Oh, well, I guess I can't use purple. Anyhow, this is an inflection point here, and the derivative here is 0. Look at that. No colors to choose from up above. And the graph here is concave down. Right? It'd be easier to see it if this graph continued, right? So it would be like that, right? So you can see it's concave down. I'm going to get this piece. Oops. Well, that piece is stuck in there. Let's write down the intervals where the graph is concave up and concave down. Right? So the graph is concave. I guess I'll start with concave up. It's concave up from B to C, and then again from D to I would list that as D to E and then E to P. Right? Even though there's no change in concavity, we do have a place where the second derivative is 0. So we'll list it as two different intervals there. And then that's it for concave up and then concave down. That would be from A to B and C to D, and last from P to Q. I wonder why they switched they skip letters from E to P on my graph here. All right, and so here we can identify that from the graph by looking for where the graph changes concavity, right? And we can identify our inflection points. We're going to be able to find that algebraically using the second derivative test. And that's coming up next. All right, so a possible inflection point of a function is an x value in the domain of f of x. So it is possible to switch concavity at like an asymptote, and then that wouldn't be there wouldn't be any inflection point, because that wouldn't be in the domain of the function, such that either the second derivative is 0 or a second derivative is undefined. These are the critical values of our first derivative. The graph of a function f of x can change its concavity at either a possible inflection point or a discontinuity. Right? So we can have changes in concavity where there are discontinuities. There just wouldn't be any inflection point where we change concavity. Right? And we'll see some graphs like that. Or we can have changes in concavity where the second derivative is 0 or undefined. So testing for intervals of concavity, find any discontinuities of a function, identify any possible points of inflection in the domain of the function by finding where the second derivative is 0 or the second derivative is undefined. Using a number line chart, that's the sign chart, test the intervals by finding the sign of the second derivative of all intervals between any points of inflection, or possible inflection point values and discontinuities. On the intervals where the second derivative is greater than 0, so if the second derivative is positive, the graph is concave up, like a cup on the interval. And on the intervals where the second derivative is less than 0, in other words, the second derivative is negative, f of x is concave down, like a frown on that interval. So let's just underline that, because that's very important. All right, let's underline that. All right, and then just like the first derivative, a number line chart can be used to determine intervals of increasing and decreasing as well as local extrema. All right, so we'll underline that too. Number line chart can be used to determine intervals of increasing and decreasing and changes in concavity. Right? So we can find local extrema using a number line and our sign chart, and we can find inflection points. Right? So finding the second derivative, of course, you take the first derivative, then you take the derivative of the first derivative, and that's the second derivative. That's why it's called the second derivative. You took the derivative twice. Concavity can change at a discontinuity such as a vertical asymptote, but it won't be an inflection point. To find all possible inflection points, find any value that's in the domain. So that just means that C is an element of the domain. That funny looking E means element. Such that the second derivative equals at that value of C equals 0, or the second derivative is undefined at x equals C, so long as f of C is defined. So the second derivative, what that's saying is the second derivative could be undefined for a certain value, but that can still be an inflection point so long as it's defined for the original function. Right? So you can be undefined for one of the derivatives. So long as you're defined for the function, then that can be an inflection point. Not every possible inflection point is an inflection value. If there's no change in sign, then there's no change in concavity, which means it's not an inflection value. Right? Just like we saw over here when we were doing the graph. Come back now, graph. There we go. So if you look at E there, E, the second derivative is undefined because they're the cusp, but there's no change in, so it would be a possible inflection value because the second derivative is undefined, but it's not an actual inflection point because there's no change in concavity. No change in concavity, you're not an inflection point. Right? Just like no change in the sign of the first derivative, it's not a relative max or min. Oops, did I go too far? Did I finish that page? Yes, I finished that page. Oh, I'll just finish reading this last little sentence there. A chart, which is our sign chart, can help you efficiently test for concavity by determining the sign of the second derivative between possible inflection values and discontinuities. So that sign chart is going to be very important for us. All right, concavity test. The graph of a twice differentiable function, f y equals f of x, in other words, f double prime of x, is concave up on an interval where the second derivative is greater than 0 and is concave down where the second derivative is less than 0. Right? So second derivative is greater than 0, concave up. Second derivative is less than 0, concave down. And we have inflection point is a point where the graph of a function has a tangent line and the concavity changes is in a point of inflection. All right, so in other words, if the second derivative changes sign, then we have a point of inflection. All right, so let's just add that to the notes. I think this is already in your notes. We'll just add this little piece of information. All right, so a point of inflection or an inflection point. Let's write an inflection point. Point of inflection just sounds a little too fancy. An inflection point is a point in the domain of the function where concavity changes. And we'll know that it exists because the second derivative will change signs at the point of inflection. Not very eloquently said, but I think it gets the point across. All right. So on the graph of the function, you'll see a change in concavity. That's an inflection point. For the second derivative, it's going to change signs at that point of inflection. Right. All right. So here we have a little visual example. All right. So here we have a function. All right. The first derivative would be positive because we're increasing. So I'm going to just make a little arrow here so I can point to what I'm talking about. All right, so right here, whoops, no, don't move, graph. All right, I try not to do this in the middle of a recording, but we're going to lock that in place. Okay, all right, so here notice that the graph is increasing. So the first derivative would be greater than 0. But it's getting less steep, but it still is increasing, right? So the first derivative, it's not increasing as quickly, but it'd still be positive values, right? Because the function itself is increasing. That's what I'm trying to say. So the function's increasing here. So the first derivative would have positive values, but they would be less positive, right, or smaller because we are decreasing at a slower and slower rate until we get right here, right? Right here, we have an inflection. We have the first derivative is going to be 0, but it's not a relative max or min because the function is still increasing. Right? This is the graph of y equals x cubed. And so notice all the way through the graph is increasing. So although the first derivative is 0 here, we do have a horizontal tangent line. It's not because there's a relative max or min, right? Because the first derivative doesn't change sign. It's still positive. It's still increasing. The second derivative is also 0, and this value here represents an inflection point. We can see that our second derivative would be changing signs. Here, the graph is concave down, so the second derivative is going to be negative. Over here, the graph is concave up. Second derivative is going to be positive. Okay, so where it's concave up, second derivative is positive. Where it's concave down, second derivative is negative. And where we change signs, this is an inflection point. Right? So often, if you'll be 0. If you have where the first derivative is 0 and it wasn't a relative or max or min, could be Not always. It could be that it's going to be an inflection point when you take the second derivative. And I think that is in your notes. So add the other information that I've written in there. I've got a little bit of information. I didn't bother to erase it. Just about the first derivative and the second derivative, right? Just to help you understand this diagram here. This is in your notes, all right? And it talks about what the first derivative tells you and the second derivative tells you. So if the first derivative is positive, the curve is rising. If the first derivative is negative, the curve is falling, right? Increasing, decreasing. If the first derivative is 0, it is a possible local maximum or minimum. Not always, but possible. If the second derivative is positive, the graph is concave up. If the second derivative is negative, the graph is concave down. If the second derivative is 0, it is a possible inflection point where concavity can change, right? And we have an example there pictured in your notes. All right, so now let's take a look at this one. This one's in your notes. I'm going to do this one with you. All right, so use concavity test as second derivative test to determine the concavity of f of x equals x squared on the interval from 2 to 8. All right, so the first thing we have to do is take the first derivative. And then we'll take the second derivative. Right, so the graph, it's f of x equals x squared. F prime of x equals 2x. That's the first derivative. Second derivative is just 2. All right, so what does that tell us about our graph? So now we'll do the step 2, which is interpret. And we don't even need a sign chart here because it's 2. 2 has no x's in it. There's nothing for me to plug into. All right, if this were a 2x and it had an x in it, we'd plug values in. But this is 2, and 2 is always a positive number. So we're going to interpret the second derivative now. And this is one, if you get a constant for your second derivative, you don't need to do a sign chart. You can interpret it from the constant because since it's positive, f of x is concave up everywhere. And think what the graph of y equals x squared looks like. You know that that's concave up. Because, so that means including on the interval to 8. So maybe we'll just put including to 8. Because f prime of x is always positive. And that's that. That was a pretty easy interpretation, right? Right, so that one's in your notes. The next one's in your notes, but it's mostly typed. I'm just going to add a little tiny bit to it. All right, so we're going to find all points of inflection. So here, we didn't have an inflection point because we have no change in concavity. It's always positive. But not true for this one. We can find an inflection point here. So we're going to find all points of inflection on the graph of y equals 2e to the negative x squared. All right, so we have to first find the derivative. The first derivative, and we would just take it's just 2e to the negative x squared, an exact copy, times the derivative of the negative x squared. So this right here is just the derivative of negative x squared, and that would be negative 2x. Right? So our first derivative is 2e to the negative x squared times negative 2x. We can multiply the 2's together, and we should move the x in front of the e. So we have negative 4x e to the negative x squared. So now we'd have to use a product rule. The first is negative 4x. The derivative of negative 4x is negative 4. Boy, that's messy. You can add this part to your notes. Oh, I guess I forgot I locked it in so it wouldn't erase. Well, that's not much better, but let's see. I guess that's a little better. All right, the second term is e to the negative x squared. And guess what its derivative is? negative 4x e to the negative x squared, right? We just took the derivative of e to the negative x squared, right? Oops, does that have too many? That should be negative 2ex e to the negative x squared, right? Because the derivative of 2e to the negative x squared, that was negative 4. Uh-oh. All right, let me fix that. I will unlock it. Oops. Unlock. We have slight boo-boo here. This should be negative 2, right? Because if we, here, I'll do it over here. So if we have e to the negative x squared, that would be an exact copy of e to the negative x squared times the derivative of negative x squared, which is negative 2x. So that's negative 2x e to the negative x squared. That had one too many 2's in there. There's no 2 in front of e to the negative x squared. All right, but the typed part is correct. All right, so our second derivative, we have the first term times the derivative of the second plus the second term times the derivative of the first. All right, so we have negative 4e to the negative x squared. That would be the derivative of the negative 4x times the term e to the negative x squared. So they did the derivative of the first times the second, and then plus the second term, excuse me, the second times the derivative of the first, that's this part here, and then the first times the derivative of the second. So that would be negative 4x e to the negative x squared times negative 2x. And that will simplify to 8x squared e to the negative x squared. We can factor out a 4e to the negative x squared, and we're left with negative 1 plus 2x squared. You want to factor out that greatest common factor. Right? So now we set them equal to 0. If you set 4e to the negative x squared equal to 0, there is no solution. It's an exponential. It's always greater than 0. This is exponential growth. It looks a little like that, and it has a horizontal asymptote at 0. Right? So no solution. It's always greater than 0. Right, then we set the second one equal to 0. Negative 1 plus 2x squared equal to 0. I would solve using solving by square roots. Let's add the 1 to both sides. So 2x squared equals 1. Divide by 2. So x squared is 1/2. And then positive and negative square root. So x is equal to positive and negative square root of 1/2. That can look a little messy. It can kind of look like 1 divided by 2. Square root of 1 divided by 2, that's 1/2. So I think you should make that 2 radicals and rationalize. So we would have x equals plus or minus the square root of 1 over the square root of 2. We'll rationalize that. So x equals positive and negative. That would just be the square root of 2. And then divided by 2. So these are the possible inflection points. Then we would do a sign chart with those. Right? So we have the smaller one is negative 2 square roots of 2. So here's our sign chart. So by the way, add all the writing parts to your notes. Right? And then that one is 0, right? Because that was a 0. And then we have square root of 2 over 2, and that was a 0. And we have to check out values in between. Well, a great one to check out in between would be 0, right? That's a good one in between. And then something smaller than negative square root of 2 over 2. How about negative 2? That's definitely smaller than that. And then here, how about positive 2, right? So we want to make sure we have values greater, smaller and greater than. All right, so let's plug in and we plug in those values into the derivative. You don't really care what the value is, you just care what the sign is, all right? So if we plugged in 0, and I'll write it down, plug in 0, so we have, and I'll use the factored version there. So this part here really doesn't make a difference, right? This one is always positive. Right? So it doesn't really, I don't really care what the value is. I just know it's greater than 0. So we're not going to bother plugging into that one. Right? Let's plug into the other part. That's the part that really matters. So, and that would be the -1 plus 2x squared. All right, so now if we plug in -2, this would be -1 plus 2 times -2 squared. That's going to be, I think I need a parentheses there. That's going to be -2 squared is 4 times 2 is 8 minus 1 is 7. Right? That's positive. So that means this is positive. If we plug in a 0, right, so that's going to be positive no matter what. -1 plus 2 times 0 squared. That's going to be -1 plus 0, which is negative. So that's negative. And then if we plug in the, oh yeah, that's right, we're plugging in these values. Hold on. Plugging in a 2, I lost track of which numbers I was plugging in. Plug in the 2, we have -1 plus 2 times 2 squared. Well, that's going to be 7 again. That's positive. All right, so, yeah, I'll write it above. We can see that the graph changes signs at the negative square root of 2 over 2 and positive square root of 2 over 2. If we plugged back in the values and actually if we've plugged back the values in, the -2 square roots of 2 and the 2 square roots of 2, back into the original function, we would get the y values that go with our inflection points. So these are the inflection points right here. Right? This one comes, this is where the second derivative equals 0. And then this part here is just, you just plug it back in, right? So this is just f of negative square root of 2 over 2. Right? And the same thing here. The second derivative equals 0, and this is just f of the square root of 2 over 2. Right? Right? And if you have any questions on these, just email me and I can go through them with you. Let's do maybe one more example, and then I'll probably take a break, and then maybe I'll do these 3. I have these 3, and then I have a few more. Yeah, I'll do these 3. So you have them all together. I am, whoops, well, guess I can't have the one I wanted. I wanted to block out those. Just pretend they're not there. Because I have these on the other page, because I know how big my writing is, and then I cannot fit those in. All right, so we want to determine the open intervals on which the graphs of the following are concave up or concave down, and find any inflection points and justify. All right, so first of all, we're going to take the first derivative. All right, so we have y prime. And now I'm using y prime because this is written as y instead of f of x. Or actually, even nicer, let's use dy dx in this notation. So dy dx equals the derivative of 3 is 0, and then the derivative of sine x is cosine x. That's the first derivative. Second derivative, d2y dx2. Derivative of cosine x is negative sine x. Right? So we're done taking the second derivative. Now we're going to set that equal to 0 and solve. Right? So that was step 1. Step 2. We have 0 equals negative sine x. Let's divide both sides by -1, and if we do that, we still have 0 equals, and now instead of negative sine x, it's positive sine x. Take the arc sine of both sides. So arc sine of 0 is equal to arc sine of sine x. Arc sine and sine cancel. That leaves x. All right, so now we want to know where arc sine is 0 on 0 and 0, 2 pi. Well, sine is going to be 0 at 0. And actually, I'll write them. I'll give each one its own line. At 0, and at pi, and at 2 pi. And it has brackets, so it does include these. All right, so those are the 3 values, right? But you're not going to change concavity at the end of the interval, are you? No. So we can't plug in anything less than 0 or 2 pi, even though those are our three solutions there. We're not going to plug anything to the left of 0 or the right of 2 pi because it's outside the domain. Right? So this is an endpoint. Can't be a change in concavity. And this is an endpoint. So the only one that can really be a possible inflection point is the pi. All right, so let's do the sign chart. So that's step number 3. All right, so we have pi, and that was a 0. And now we need something less than pi, like pi halves, and something greater than pi, like 3 pi halves. And it has to be within the interval 0 to 2 pi. All right, so and remember, we're plugging it into the second derivative, which is right here. All right, so if we plug in, and I'll write it out for you. All right, so if we have negative sine pi halves, right? Pi halves is 1 times negative 1 is negative 1, so that's negative. Negative sine 3 pi halves. 3 pi halves would be negative 1 times a negative 1 is positive 1. So that's going to be positive. Right? So now we can, step 4, we're going to explain where it's concave up, concave down, and then find our inflection points. We're just justifying where the graph is concave up, concave down, and then justifying the inflection point. Right? So y equals 3 plus sine x is concave up on pi 2 pi, and I guess we can put a bracket there because that's the end of the interval. Pi 2 pi because and I'll use f prime. I'll put d2y. I'll put exactly what I put over there. Usually I write f prime, f double prime of x. d2y dx2 is greater than 0, and concave down on, and it was concave down from 0 to pi. And we could actually put a bracket there because that ends the interval. 0 to pi because d2y, or you can just put the second derivative, dx2 is less than 0. There is an inflection point. Let's find the y value. I'll just leave a blank here. I'll put that y, the whole point in. At because second derivative, I'm tired of writing, I'm running out of space. I'm tired of writing the other thing. Changes sign at x equals pi. Oh man, just put that in. Let me scroll the screen down just a little bit. Or up, I should say. All right, let's find the y value that goes with that. All right, so it was y equals 3 plus sine pi. At pi, sine is 0, so y equals 3. And so our point here would be pi 3. But basically what this is just a sine graph shifted up 3. So it changes sign, it has an inflection point there at pi 3. All right, that's our first one. Should I do one more? Let's do this one. All right, determine the open intervals on which the same directions. All right, there's our next one. Now I can do this one of two ways. I can leave it as it is, or I can do the quotient rule with it. This has a -1 exponent. I could simplify the exponent. I don't know which is better. It's either going to be a product rule or a quotient rule. let's just use the quotient rule. Let's see what that looks like. So f of x equals 6 divided by x squared plus 3. Right? So either way, it's either going to be a quotient rule or a product rule. I'll just do a quotient rule, and hopefully I won't regret that. All right, so our first derivative, we have the denominator times the derivative of the numerator. Well, so u is 6. The derivative of 6 is 0. Denominator is x squared plus 3. The derivative is 2x. So that's not going to be so bad. So that's going to be 0 times x squared plus 3, which of course is 0, minus the numerator times the derivative of the denominator. So minus 6 times 2x. Well, this is not too bad. Divided by the denominator squared. So that is going to be negative 12x divided by x squared plus 3 squared. All right, there's the first derivative. Now let's find the second derivative. Again, we have to use a product rule, quotient rule. The numerator is negative 12x. The derivative of that is negative 12. The denominator is x squared plus 3 squared. I can either square it or use chain rule. I'll use a chain rule. It's not that bad. So this would be 2 times x squared plus 3 times the derivative of the x squared plus 3. So that would be 2 times x squared plus 3 times 2x, which would be 4x times x squared plus 3. And if you like, we could distribute that. Really wouldn't make much of a difference. Why not? All right, so this would be 4x cubed plus 12x. That would be the derivative of the denominator. Oh, I didn't even put a v in there. So this would be dv. All right, so f double prime. All the space on this one is going to be taking this derivative. The denominator times the derivative of the numerator. So that'd be negative 12 times x squared plus 3 squared minus the numerator times the derivative of the denominator. So that would be, now that's going to be a plus 12x times 4x cubed plus 12x all over, and we're going to have to simplify this, x squared plus 3 squared. You know, now I'm thinking I should not have distributed, because I could factor out the x squared plus 3. So I take that part back. Let's do it let's leave it like that. So that is going to be 12x times 4x times x squared plus 3. Okay, now let's factor out the, let's factor out a negative 12. Let's factor out the x squared plus 3. All right. So in the first term, we're going to be left with an x squared plus 3. And then the second term, I factored out a negative 12, so the second one's going to be now negative. So now we have a negative x times 4x. We factored out the x squared plus 3, so that's gone, all over x squared plus 3. Oh, whoops. Squared squared. This should be to the fourth power. It already was squared. All right, so now let's combine like terms and let's reduce. We could reduce this and make that x squared plus 3 cubed. And then we can combine some like terms. Continuing, equals, so we have negative 12, and I can cancel that because these are just things that are multiplied. Negative 12 is a factor, x squared plus 3 is a factor, and that mess when we combine like terms is a factor. So this would be negative 12 times, we have this part here is negative 4x squared. Let's just make this a little easier and do it all at the same time. So x squared minus 4x squared is negative 3x squared. And then we have a plus 3. all over x squared plus 3 cubed. All right. So now our next step, that was step 1. This one has a long step 1. Step 2 is to set that equal to 0. So we have, we have two things to consider. We have to consider where it's we have to set the numerator equal to 0 and the denominator equal to 0. Right? Where the numerator is equal to 0, that's where f double prime of x equals 0. Where the denominator equals 0, that's where f double prime is undefined. So we'll set the numerator equal to 0. Negative 12, negative 3x squared plus 3 equals 0. Right, well, we can divide by negative 12 and it won't make any bit of difference in the 0. So negative 3x squared plus 3 equals 0. Subtract 3 from both sides. Negative 3x squared. Actually, let's subtract the 3x squared. Add the 3x squared to both sides. We'll make it positive at the same time. 3 equals 3x squared. Divide by 3. And actually, I could have just factored out a negative 3, couldn't I? 1 equals x squared, so x equals plus or minus 1. Right? Two solutions there. Wasn't really thinking about it. Could have just factored out the negative 3. Would have had x squared minus 1. Either way, positive and negative 1 is where f double prime of x equals 0. And then we have to consider where it's undefined, and that would be where x squared plus 3 cubed equals 0. Take the cube root of both sides. We have x squared plus 3 equals 0. X squared equals negative 3. And x squared never equals negative 3. So this one has no solution. Well, it has a solution, but it would be complex. X would have to equal plus or minus I square roots of 3. So that doesn't count. Has to be in the domain. That's a complex number. That's not in the domain. So we have only 2 possible inflection points. Right? Those are our possible inflection points. And we'll do the sign chart. This one took, as you can see why I only did 1 per page. Feel free to add extra paper in your book if you need to. All right, so sign chart. This is step 3. I don't know, I just don't seem to have nice organization here, do I? Maybe if I do this for you. There we go. Okay, step 3. We have negative 1 and 1, and then those are zeros. All right, and then we need a number on either side of each of those. So 0, negative 2, and 2. All right, and we only care about the sign. Right? So, and we're plugging that into the second derivative. So right here is the most cleaned up version of the second derivative. All right, so if we plug in the negative 2, that would be negative 12 times negative 3 times negative 2 squared plus 3 divided by negative. Now, if you notice, the denominator is always going to be a positive number, right? Because no matter if I square something, it's positive. So I'm always going to have a positive number. So really, we don't even have to worry about the denominator. This is always positive. Because the squaring is going to make things positive, and then we're adding 3 to it and cubing it. So it's always a positive number. So we just have to care about whether the numerator is positive or negative. All right, so negative 2 squared is 4 times negative 3 would make that negative 12 times negative 12. That's going to be a positive, right? So if I plug in negative 2, it is positive. if we plug in -1, we'd have -12 times -3 times -1 squared plus 3. Oh wait, I have a bad use of parentheses here. Oh yeah, I guess it's all right. This whole thing is in parentheses. Let me just double check that again. So this would be 4, -12 plus 3 is -9 times -12. Yes, this would be positive. All right, so now I need to put my parentheses in correctly. -1 squared is 1 times -3 would make that negative. Oops, sorry, I plugged in the wrong number. Not -1. No, that's going to be 0. 0. All right, and so this is 0. All right, so that would be 0 times plus 3 would be +3 times -12. That's going to be a negative. And then if we plug in 2, probably get the same thing as we did when we got -2. All right, so f double prime of 2, -12 times -3 times 2 squared plus 3, and that's all in parentheses there. So that would be -12, that would be -9 times -12. That's going to be positive. All right, so finally, step 4, and that is to interpret. And I'm going to take a break after this one. All right, so f of x is concave up on -infinity, because the whole interval, so it goes from -1 to all the way down to -infinity, and it goes from 1 all the way up to infinity. So -infinity to -1, and then again from 1 to infinity. Right? At the inflection points, it changes concavity. And that's because f double prime of x is greater than 0 on this interval. F of x is concave down. On, and that is from -1 to 1, because f double prime of x is less than 0 on this interval. There is an inflection point. Oops, I put the eraser in the wrong spot. And I'm going to move the screen up just a little bit. And it's at, or I should say, there are, there's more than one, there are inflection points at, so we got, if we plugged in the -1 back into the original function, which is way up here, right, so f of -1 would be 6 over -1 squared plus 3. That would be 6 over 4, or 3/2. And f of 1 is the exact same thing. So let's finish this part up. At 1 3/2 and -1 3/2, where f double prime of x changes sign. Right. Whew, that took a lot of space. All right, well, pause the tape, rewind it, whatever you need to be able to write that one down. This took up a lot of space. I just want to go back to the previous one just to make sure that I didn't stop writing before I stopped talking. So that's fine. I was just looking to make sure I had the whole interval in there. And on this one, I didn't write it in. It was already written in. So that was it. Okay, just wanted to make sure I had the entire interval. Sometimes when I'm writing and talking at the same time, I don't write down exactly what I say, but I did. All right, so we're going to pause this tape because it's 50 minutes, holy moly, and then I'll pick up with some more finding the inflection points. Thanks for watching. Bye for now.